Okay, I think we're ready to start. So, hello everyone. This is going to be our last colloquium this fall, and I'm really grateful to all of you for your participation and promotion of our colloquiums. So without you, all of this, I would say, would not be possible. And I will do my best to continue these colloquiums, at least for the next semester. So please stay tuned. The speakers and the topics for the next semester will be announced pretty soon. Today, we're diving into the topic, which is the charge transfer theories and electrocatalysis. So let me make a very short introduction into what is the scope of this colloquium is for today. So these days, you probably noticed that the electrocatalytic activity of a solid is commonly explained using DFT, which can calculate the surface properties and the thermodynamics of adsorption. However, one significant limitation of this approach is that it does not address the kinetics of the electron transfer. And that kinetics is vital for the calculations of the reaction rates, obviously. So because the kinetics is not accessible in pure DFT, we can see a lot of thermodynamic descriptors that are important and are supposed to predict which electrocatalysts are the best. Another important aspect to mention is that based only on thermodynamic quantities, you cannot properly explain the physical mechanisms for the reaction. At best, you can only probably simulate the processes at the atomistic level and just see what's happening. But saying why that's happening is might be pretty tricky. Now, there is an alternative approach, which is to use an alternative to DFT, which is to use the theory based on modal Hamiltonians that can offer a proper treatment of the kinetics of charge transfer. And most importantly, this approach can offer this missing insight, the link into how the electron and ion transfers occur in electrochemistry. So today we're hosting Professor Elizabeth Santos from the Ulm University, who is an expert in the theory of electrochemical charge transfer, including modal Hamiltonians and the Green's function approach and techniques. So Elizabeth received her PhD at the National University of Cordoba in Argentina. Then she spent several years as a postdoc at Bonn University in Germany. And afterwards, she held various positions as a researcher and professor on both sides of the Atlantic, working on both experimental and theoretical aspects of electrochemistry. Currently, Elizabeth is an independent researcher and a full honorary professor at the University of Cordoba in Argentina. And I cannot help but mention that she is also the co-author of one of my favorite books, which is called The Interfacial Electrochemistry. So Elizabeth, thank you so much for joining us today. Now the stage is yours.
Thank you very much for the nice introduction. And okay, then I will start with my talk. I give my screen free. Should be this one.
Mm-hmm.
And then I start. It's okay? Yeah.
We don't see yet.
No? Ooh. Ah, okay. That. Oh. It's coming. Oh, I don't know why it is not possible now. It was possible before.
Yes, it works. So now you can start the presentation. We'll see if it shows the slides as it should.
That's right.
Yes, we're on the second slide now.
Okay, right now. Okay.
Thank you.
Okay, good. Then my talk from today is about electron transfer, and I will focus at electrochemical interface because electron transfer reactions is a very wide field, and but I focus to electrochemical interfaces. And my talk First, I want to give some basic concepts of electrochemical environment, especially about properties that which are measurable and which are not. And then I will go to electron transfer reactions and show how we can classify that according to where the reaction takes place or the strength of the interaction between the reactant and the electron. An important issue is also we have a Rayleigh constant, and we have not only the activation energy, but we have also a pre-exponential factor. And then I want to mention some things about that. Then I show you the different models of electron transfer at electrochemical interface that are in the literature. And later show some examples and electron transfers at different electron materials and different reactants. And then I will talk a little about these descriptors and the qualitative analysis using correlations or Volcano plots. And then at the end, I want to discuss with you which are the perspectives or to improve and to learn more about electron transfer reactions. Good. We go now to the electrochemical environment. Here I show you all the properties that are characterized in an electrochemical interface. This with the work functions is also a property that is very useful in surface science, not only in electrochemistry, and is defined as the work that we have to do to take an electron from the bulk of a metal to just outside of the electron. And then we have, this is the work function is a measurable properties. Then we have this inner potential, which is not measurable, and the outer potential that is measurable. And then we have this surface dipole potential, which is not measurable, the chemical potential, which neither is measurable, but the electrochemical potential, it is. And then these are all the relation between these properties. We see here, for example, that the work function is the opposite of the sum of the, we have to do in order to take an electron, not only with the chemical potential from the electron in the material, but also we have to go through the surface dipole at the interface. And good, then we have all this relation. I think it's clear and are also explained in our book. Axel Gross had also talked about that, and I think my talk will be some complement of that. Then, what is an electrochemical environment? There are different models about the double layer, no? And then we have, this is we have at the interface between an electrode and the vacuum or the solution, there is a change in the electronic density, and this can be also seen as a split between a charge of the solution side, for example, and the image charge at the side of the metal. This is but we have to have keep in mind that this is a picture. No? The reality is not so like this. We have actually the chart is distributed between at the interface between the electrode and the solution. And in this sense, it's nice from DFT that we can calculate electronic charge difference between the components of a system. And for example, here are shown for the adsorption of chloride on gold, and we see this is the charge distribution. Red is a accumulation of electron, blue is a depletion, and we see here how it's formed a sort of dipole. And we don't see the chloride had a -1 charge. And then when the coverage increased, there is a more complicated distribution of the electronic charge. We have here a depletion, and we have this play within that the interaction is in some way screened between the adsorbate. If we put now the solvent, this electronic distribution is still more complicated. And if we have a more reactant that's more complicated than chloride, for example, cysteine adsorbed on silver, then we see that this, according to the distance to the interface, how the electronic distribution changed. Then in this, there is also a very nice concept in electrochemistry that is called electrosorption valency, which is something that we can measure, that is related to the partial charge transfer, which is something that we cannot measure. But this is what partial charge transfer is in our idea, what we see. We think if a reactant that cannot give the total electron to the electrons, for example, then we have here a fractional number of electrons that are transferred. But what we can measure experimentally is the change in the charge of the metal with the surface excess of a given species that is absorbed. And the relationship with this between this electrosorption valency and this partial charge transfers depends of a physical model. For example, here is one of them. We have this geometrical factor G, and then we see here that this charge that we measure is not the partial charge transfer. It's related to that. And then only in some cases we can see a total discharge or incorporation into the electron, or when there is no charge transfer, that's this lambda with this electrosorption valency are equivalent. Then we see all this, also the electrosorption valency depends on the coverage and on the potential. And there are very nice literature here, a lot of work that has been done in this direction. And if you are interested in, you can take a look at this literature. This should be perhaps a topic for another colloquium. Good. Then here we come to destroy one of the first myths that in electrochemical environment. This simple picture of a double layer, for example, here from Wikipedia, where all the water at the interface are oriented in the same direction. A simple electrostatic estimation, which should give you a potential drop across the interface of about 7-8 volts. That is impossible. And then that we have to forget this picture. This is coming always. I think Axel Gross had already told that this is not a good model, but it's come again and again. And then I say careful. Good. Another thing, within electrochemical environment, one reaction that's very frequently is taken as a prototype for an electrocatalytic reaction is the hydrogen evolution reaction. But this is because the people say it is a simple reaction, but actually it is not so simple. We have many steps for the reaction, depending on the material. We can have one mechanism or another one. And for example, also this proton actually if we are in an electrochemical environment, for example, water. This is not as a proton, but this is as a Sundel or a hydrion or Eigen's ion. No? Then what we do with DFT, which we can very good, is, for example, follow the adsorption of the hydrogen atoms or the dissociation or formation of the hydrogen molecule. But all these complex things that occur in electrochemical environment is not so easy. There are many intents, but it's not so easy. Good, then we come now to electron transfer reactions. We have to consider in our system, we have the electrode. It's important to know the electronic structure of our electrode. We have a solvent, and we have the reactant that could be an ion, that could be a molecule or something else. And then it is important to know also the electronic structure and all the interaction between this part of the system. Then here is the first classification of electron transfer reaction. If we think where the electron transfer reactions take place in an interface. If this is far away from the interface, that are called this outer sphere reaction, for example, redox couple at the methyl electrode, experimentally we see that there is no dependence with the electron material. These reactions are the rate constant is similar for all the type of electron. On the contrary, in the case of inner sphere reactions, for example, hydrogen evolution reaction, then, there is a very strong dependencies with the material of the electron. And we see here there are many orders of magnitude between the different materials. Another very useful classification of electron transfer reaction is according to the electronic interaction between the reactant and the electron. We have a range here when the interactions are very, very low. That the rate constant depends on the material. Then we have an intermediate regions where there are no dependencies, and then at the end, when the interactions are very strong, we have again a dependence with the materials of the electrode, and this is a region of we call the electrocatalysis. We shall call again to this plot because this show very nice the different tendencies. Good. Now to the pre-exponential factor and activation energy. According to Arrhenius, the rate constants, we have the pre-exponential factor and the activation energy. In the case of electrochemical system, we measure a current that is proportional to these rate constants and the concentration of the reactor. The question is this pre-exponential factor and the activation energy. How much depends on the electron material, on the dynamic of the solvent, on the overpotential, and unfortunately, the experimental results are highly contradictory, especially in the case of inner sphere reactions, because it is not easy to measure both of them, to obtain both of them for experimental data. And we must be careful with this. And the experimentalists should try to find better method to obtain these two parameters. This is why it's too complicated, because in order to have these two properties, we have to separate the contribution of the different individual steps. We must be sure that we are determining the right step Then there are some dark ghosts, bad ghosts that disturb the interface. For example, the anions or cations that can absorb specifically, and then we measure that, but it's not only one reaction, but we are seeing the effect of the co-absorption of anion. There are also could be double layer effect, or sometimes we measure a rate constant, but how we can separate both this pre-exponential factor and the activation energy. And sometimes there are some compensation effect between both of them. Good. Then we focus now in the pre-exponential factor. In the case of outer sphere reactions, this is related to the this frequency factor, which is the frequency of a reactant when go from the reactant to the product, and this is the effective thickness of the region where the reaction takes place, and that is usually a few angstroms, not so large. And good. In the first approximation, for example, Marcus used based on the collision theory, proposed the value for the pre-exponential factor of 10 to 4, 10 to 5. And, but also we can use classical transition state theory, and then we have here the oscillation of one mode or the multi-dimensional from the well of the reactant, and also from the transition state. We can take into account the dynamics of the solvent reorganizations, for example, through the Kramer theory. But also in this case, if we consider that in the most of the cases, this term that we are multiplying the others is almost 1. Then we obtain a pre-exponential factor that are almost in the same order of magnitude as the original proposals by Marcus. But we have to consider this, what happened here. We have a reactant, and we have an inner sphere solvation and an outer sphere solvation. And how they relax could be very different. The inner sphere is much faster, the reorganization, than from the outer one. And then here we can separate this reorganization energy from the inner sphere and the outer sphere. And depending on the frequencies, if we have in the classical limits, where this is much smaller than the thermal energy, we see that because that is faster in the inner sphere, the rate can be enhanced. But we must be careful, because sometimes this enhancement makes us the trajectory are not through the saddle point. This is this saddle point avoidance, and then the activation energy is larger. And we have the pre-exponential factor that is larger, but a larger activation energy makes so a sort of compensation of the rate constant. And then we have the quantum limit when the frequencies are much higher than the thermal energy, and then could appear tunneling effects, and we have to consider the Frank-Condon factor, and these are usually very low, and then the pre-exponential factor becomes smaller. And another thing that to take into account the pre-exponential factor is in the case of non-adiabatic reactions. We shall see what are the non-adiabatic reactions. This factor depends on the electrode materials, not only on the dynamic of the solvent. Then summarizing, please don't forget the pre-exponential factor. We must not analyze only the activation energy, but also the pre-exponential factor. Good. Coming back to the electron transfer reactions. The first theories were proposed by Marcus and Hash in the 50s. And in this case, is the Frank-Condon principle is applied, that electron transfer is fast compared to the solvent movement, and then therefore the electron transfer is determined by the reorganization of the solvent. And the electron transfer is isoenergetic. Then we assumes so an harmonic oscillator approximation of this rearrangement of the solvent around the reactant, and consider a parabolic potential. And then we have the charged, this is a charged species, and we have then we can define also introduce a normalized solvent coordinate that we shall call Q, that is defined as the opposite of the charge of our species. And for example, if we have an electron, this is the electron that will be transferred in the initial state, we have no charge species, and then after that we have a final state where an electron has been transferred. And then we obtain this sort of potential energy surface. An important property here is this lambda, that is the solvent the reorganization energy of the solvent. And this is for the case of equilibrium, delta G is 0. And for this case, the initial and final state, for example, we can take as example the redox couple iron +3, iron +2, and we have here the minimum of for the iron +3 for the solvent reorganization is at solvent coordinate -1. The final state Q equal 0. And then we have this parabola is described for the oxidized state by this equation, and it is for the reduction state. And then we see here that the activation energy at equilibrium is the solvation reorganization of the reorganization energy for the solvent divided by 4. Then what happens if we have different, we are not in equilibrium? Then the activation energy have an additional term, have this form, and then when we increase and increase this delta G, we come to a situation where these both parabola cross at where this is at the minimum. And at this case, we have an activation energy of 0. But then comes an interesting question. What happens if the free energy increase and increase? We can have this situation, and then we see here as again an increase of the activation energy. And this is what is called the inverted region. And this occurs when the delta G is larger than the reorganization energy. And indeed, this had been observed experimentally in the case of homogeneous phases. This is for these intramolecular electron transfer reactions. This is one of the many examples that you can find in the literature. That the rate constant first increase and then decrease again because this cross of the parabola. What happened now? But we are interested in an electrochemical interface. And then the electron transfer here, we have to replace one of the couple redox by the electron. And here appears also the overpotential, that instead to have this free energy, good, it is related to the overpotential. And good, in the equilibrium case, that means when the overpotential is 0, we have again the same, the activation energy like in the homogeneous phases. When we increase the overpotential, then we are moving this from the Fermi level, and then we see that also this activation energy depends on the the overpotential, and I'm sorry. Here we see that if we change the overpotential, change of the activation energy with the overpotential give us the charge transfer coefficient, and this is when near the equilibrium the charge transfer coefficient is 1/2, but when the overpotential is larger, then could be different from 1/2. And then now come the questions. If we do that, increase and increase the overpotential, we have here the activation energy is 0. What happens if we increase more? We obtain also an inversion region. And the answer in the case of metal is no, because we have enough electronic level in the size of the metal where the electron can go, and then in this case, up to a point, the activation energy is always 0, but not increase anymore. That means that our Tafel plot looks like that. Obviously, that depends on the value of the reorganization energy, but at a certain point, it becomes the right constant becomes constant, and there is a range where we have that is almost 1/2, but then the alpha coefficients decrease to 0. And then that is electron transfer. We compare between homogeneous phases and electrochemical systems. In the case of homogeneous system, we can have the activation energies increase again up to a certain point where the free energy is near the reorganization energy. But in the case of electrochemical system, it doesn't occur. It's always 0. And this is one of the second method, but you can find in the literature many contributions that say they have found in metal electrode the inversion region of Marcus, and in electrochemical systems with a metallic electrode, it is not possible. That is other thing if we have a semiconductor, because then we don't have this electronic level over the Fermi level, but in the band gap. But for electrodes, metallic electrode, this region doesn't exist. Then come back to the electronic interaction. We have seen we can have weak interaction, strong interaction in the case of electrocatalysis, and if we have a very weak interaction, the electronic level corresponding to the reactant is delta Dirac, have the given energy, energy, but if there are interactions with the metal, this level, there is a broadening of this level. And this had to do with, it's similar what we have said with the broadening lines in spectroscopy. And that have to do with this lifetime, how long state the electron in one state or the other. And then these are these chemisorption functions that we have come back later. Then, if we have this broadening of the electronic state of our system, obviously, when we approach to the methyl, the interaction are larger and the broadening is larger. And also, there could be a shift of the position of the center of these electronic levels, and that makes a change in the occupation of these orbitals. That means the occupation will change. And then, how we can evaluate or estimate these chemisorption functions that are related to the interactions with the electronic state of the electron. A nice approximation is to use the Anderson-Newns model for the density of electronic states. This has this form where here we have this delta chemisorption function and this sigma that are related between them. But this is mathematical relation. But in the case when we have a constant, when the interaction doesn't depend much more from the electronic energy, then it's constant, and then this has the form of a Lorentz. The electronic structure of the electrode can have different shapes. We can use idealized models for the bands of the electrode. We can use the wide band approximation and assume that the electron has a constant density of electron, or a semi-elliptic model. We can have, in the case of semiconductor, also the many semi-elliptical bands separated by the band gap. And if we have some defects, we can introduce in some way through this idealized band. In the case of graphene, is the structure of the electronic states are different, and also if we have defects, appears some state between in this band gap. Could real bands or calculated from DFT looks like this, are not semi-elliptic, they don't have semi-elliptical form, but for some in some cases is the description through this idealized band is good enough to predict some properties. But these are in the case of semiconductor. We have always a band gap, and good. Then this, in the case of the interaction, depending if the interaction are weak, we can have this Lorentzian form of the distribution of the electron. But if it is strong enough, for example, through the interaction through a D band, it can appear here states that can be associated with bonding and anti-bonding state between the reactant and the electron. Okay, then in which way we can describe that? We have seen, we have the component of our system, the electrode, the solvent, and the reactant. We can have a Hamiltonian where we're taking into account the components for every of these components, and also a term that take into account the interaction. And use these very elegant green functions that allow us to calculate the energy. Good. We come here again to this plot. In the case of the how we obtain these different dependencies, we start with this part, that's the Marcus hash, where the rate constant doesn't depend, that means this term must be constant. And then in this weak adiabatic electron transfer process, we obtain for the rate constants expression like this. And here we see we have electronic equilibrium, and the activation energy that depends only on the reorganization energy of the solvent and on the overpotential. This is in the case of weak interaction. And the reaction rate is independent of the electroproperty of the metal. Then, in this case, in this Marcus hash region, here is the Hamiltonian. We have a component that takes into account the reactant, the states in the electrode, the solvent, and then the interaction between the reactant and the solvent. And for this case, the important interaction is between the solvent and the reactant. And okay, we can reorganize a little this expression and put together this is the occupation of the orbital for A, and we define this epsilon that is depends. This is when far away from the surface and when the solvent neutral state, but this we can move by this perturbation of the solvent can move this state in this way. With these are the interaction with the solvent, and for example, in the case here. We come from we have an oxidation reactions. We have this parabola that we have seen before, but now we can analyze what is the electronic energy. In the case of here, we have at the very beginning, we start here at minus lambda for the electronic energy. And the total energy is minus lambda. When the system goes to the transition state, here start to be charged, and then here we go from the electronic energy to lambda, but because there is this solvation. Increase the solvation of the charge increase, then the activation energy is less than lambda. And the end, when we go to the final state, we come again to minus lambda in the equilibrium. And then this difference to lambda, actually, this is electronic energy, and this is the total energy taking into account the effect of the solvent. And with this state dependence, this variation of the solvents can produce the occupation, or that also in the case of the potential, we can move the position of the electronic level of the reactant. That means now we go to this region. This is the non-adiabatic region. And in this case, it is used, in the case of weak, is the interaction very weak, then we can use in the Hamiltonian first order perturbation. And we don't have electronic equilibrium. That means the system can go to the up to the transition state, but come back not every time that the system reach the transition state, go to the product. And then in this case, here appeared the dependence with the interaction with the electrode appears in the pre-exponential factor of the Wright constant. In the activation energy depends only on the reorganization of the solvent and the overpotential. But the dependence with the materials, properties of the material appears in the pre-exponential factor. Here we can obtain also our Tafel plots, and they reach also a constant value for higher overpotential. And here it's interesting to say some words about this Gerischer interpretation. In this case, Gerischer had the idea that we can separate the expression for the Wright constants in a term that he called probability to find an occupied state in the solution, that had the form here you see is some of a Gaussian function, and the product of this probability with the Fermi-Dirac distribution give us this Wright constant. Here, if you see that this is I say again, it's probability to find an occupied state in solution, and then take into account how move the level, that is a delta Dirac, because the interaction are very, very, very weak, how move it by effect of the reorganization energy of the solvent and the overpotential. And what we can find in a similar expression for the oxidized state and reduction state. And they look like this. And here, these are this Gaussian, this is distribution, how move the electronic level. And here, I have to say this other myth that is wrong. The people, many papers appear these functions, they call that density of electronic state, and they are not density of electronic state. It's the probability how it is moving the level of the state by effect of the solvent, but it is not a broadening like we have seen before for the electronic state due to the interaction with the material. Then, good, that was this part. Then we go on this curve, and here, when the interaction are weak, but not so weak that we have this broadening of the electronic state like a Lorentzian, then in this case appear an extra term that is due to the interaction of the reactant with the electrode that has this form, and if we consider that the electronic distribution in the electrode is constant, it is wide band approximation, and then here our potential energy curves then becomes not so sharp. There is a slight decrease of the activation energy due to this term. And then here again we can have with this broadening that with the potential or the oscillation of the solvent can change the occupation of this state. Okay, then we go to the last part of the course. This is the electrocatalysis part. And then here is when we have very strong interactions. And here appears in the activation energy. This is the total energy system appear depends of the interaction with the metal. And we have here, again, electronic equilibrium. And now the activation energies depend not only on the reorganization of the solvent, but also on the properties of the electron material, and obviously also on the overpotential. And then we have now, instead to have this two-dimensional potential energy curves, we have potential energy surfaces that at least two-dimensional. And then we can define at least these two coordinates, the solvent coordinate and the distance to the electron, because the interaction change when the reactant approach to the electron. And also with the solvent, it can be occupied or unoccupied. That means instead to have this potential curve, we have surface this sort of plot where one coordinate is the solvent coordinate and the other is the distance to the electron. And then we can look there for the activation energy and so on. Good. Then summarizing this part with the different electron transfer reactions. We have, according to the kinetic regime, in the case of non-adiabatic, where we don't have electronic equilibrium, the pre-exponential factor depends on the electronic property of the electron, and the activation energy only on the reorganization energy of the solvent. In the case of weak adiabatic interaction, that we are in the case of Marcus and Hash, the pre-exponential factor depends only from the, is determined by solvent friction, that will not depend on the material, and the activation energy also, it doesn't depend of the material, only on the reorganization energy. In this case, neither appears the electron material properties. And then we are in this region where, independent of which electron we have, the rate constant is the same. In the case when the interaction becomes larger, but not so large that we can use the wideband approximation, we have electronic equilibrium. The pre-exponential factor does not depend on the material, but in the case of the activation energy, we become a slighted dependence of the material. And in the case of electrocatalysis with strong adiabatic interaction, the pre-exponential factor does not depend of the material, depends only of the dynamic of the solvent, and the activation energy now depends very strongly on the electron material. Good. These were very simple electron transfer reactions. We can have also electron transfer reaction involving bond breaking. And with the first approach were by Kuznetsov and Fabian, and they consider in the case of the non-adiabatic limits, we can consider one potential energy, potential curve for the reactant and other for the reactant, for the product. And in this case, what we obtain is that activation energy is expression similar to Marcus' case, but now we have here the dissociation. This is the dissociation energy of the molecule appears as an extra term. That means the activation energy is not only this reorganization energy, but also is have to do with the dissociation energy of the molecule. Later, Copper introduced treat the system look like with a Hamiltonian, but put for the interaction between the atoms of the molecule an effective switching operator. Describing the bond breaking process. When the occupation is 1, this term disappears. When the occupation is 0, this term disappears. And then this is a switch between these two potential curves. And also, he can also introduce the interaction with the method, and then appeared also this term with the wideband approximation that come in the activation energy. Later, with Wolfgang Schmickler made this for the non-adiabatic limit the case when tunneling is possible. And then they obtain for some cases that when tunneling is important, the activation energy decrease for effect of this tunneling process. And with later then is Anna Ignatiuk, they in the adiabatic limit, he have also again these two curves, but then she doesn't use anymore this Morse potential, but calculate this curve for a given system, for example, for this the dissociation of this molecule with DFT using Gaussian approach, and then do with this potential energy curve the molecular dynamic, and obtain the whole base for the reaction. And they agree with experimental data were very good in that case. And then, but then later, together with Mark Copper, we use our Hamiltonian and put this interaction instead to have this effective switching operator. We don't consider anymore, but we put an interaction between the atoms that depends on the distance between the atoms, and they have a form similar to the Morse potential, but we can describe without the use of this switching operator. And then we have when we have the molecule, we have a bonding and anti-bonding orbital, and when the distance between the atoms increase and increase, they collapse in one level that corresponds to the atoms, the separated atoms. When we have weak interaction, we can consider also electronic levels like delta Dirac. And if the interaction with the system is larger, we can use also wideband approximation, for example, and have this Lorentzian form for the density of states, where we have bonding and anti-bonding orbital described with the interaction with the solvent that change then when the when the molecule approach the electron. And then we can obtain also this potential energy surfaces, and depending if we have a dissociation or a reduction or an oxidation, here is the solvent, the solvent coordinate is here the distance between both atoms in the molecule. We have different shapes for these potential energy surfaces. When the interactions are stronger, for example, by a D-band, we can have also the formation of, for example, here we have this is for an oxidation or for the reduction reaction. When the molecule, we have bonding and anti-bonding for the molecule. When it becomes near to the electron, one of these orbitals interacts strongly with the electrode, and we have here bonding and anti-bonding, but between the molecules and the electron. And at the end, we have only one orbital corresponding to the isolated atom. We obtain this potential energy surface. This is where, in the case of the wideband approximation, interactions are larger, the activation energy, of course, becomes lower. And the last, or another view, completely different, is we use the same Hamiltonian, but it's from the physics. We use this Lanczos transformation, and also with the Green functions. But then what we can associate this molecular dissociation as a form of quantum dynamical phase transition, which is related to the an analytical discontinuity due to virtual state. The virtual state becomes a localized state. This is a more complicated view, but if you are interested in, you can look at this paper. Actually, at the end, the results are the same, only the view is some different. Good, I think now we can do a short break. And if there are some questions in between.
Thank you, Elizabeth. Just a second, I'm gonna, so if anybody has any questions, please go ahead and ask. So we have some time, maybe a couple of minutes for a few questions, and then we will continue. We'll have a second part afterwards. So please, if you're interested, make sure you stay through the Q&A part. So please go ahead and ask questions if you have any. Maybe I can just start. So this is pretty normal. So we, you've been discussing the theory of the charge transfer from the point of view of from the reactant point of view. So if the reactant is really small, so say I have a proton, do you have to, because there are a lot of theories that do take into account the quantum nuclear effects. So when, for example, you try to explain the HR reaction, do you have to really take them into account into the theory itself? Because as far as I remember, it was probably not taken into account, right? So you just treat the proton as just a cation.
Good. We have the reactant. What we take into account are the electronic levels of this reactant, right, and how interact this with the electrode. I don't know exactly what do you mean with the. So,
but it gets solvated, right? So during the solvation itself, the quantum nuclear effect, meaning that the proton tunneling effect, is it something that you have to take into account?
Yes. In the case of the tunneling, actually, like our potential energy surfaces look at. This should be possible if the transition comes perpendicular to the solvent coordinate. But in most of the case, I will show later some examples, it is not the case. And then the tunneling probability could be, but it's not so strong because the transition goes more some more parallel to the solvent coordinates. That's the part. But this is a point that could be, but I think this should be not so important contribution.
So would it be possible to say that the theory works better for bigger cations on anions, especially the bond breaking theory? So the bigger it is, the more well-defined sort of the uniform solvation is. Because the smaller it is, then the more specific it becomes. So there you have a specific coordination number and so on.
Yes, I think so. If it depends how you can model this solvation shell. No? We have used here the simple form that's with the reorganization energy. We consider this parabolic interaction with the solvent with the particle. That is what we have used. But there are some more complicated interaction with the solvent. This theory doesn't take into account.
Okay, one question from the chat is if you can explain, it's regarding the Marcus theory, how do you calculate the electronic coupling between the diabatic states?
we use the Anderson-Newns model to calculate the coupling constants. Then in some examples that we show in the second part, perhaps you can see better that. In the case of Marcus, the region where there is no dependence on the electropotential, there are not we don't consider any interaction between the metal or the electrode and the reactant. It comes when there are a weak interaction, then we use Anderson-Newns to describe how is the broadening of the electronic states of the reactant.
Right. So another question is, how do we calculate the reorganization energy from MD that samples certain geometries? So maybe this is something that you will be discussing later, I guess.
Yes,
right?
Later I will show how because here we use as a parameter lambda, the reorganization energy, 0.5 electron volt, and so on. But this is where parameters taken from parameters that are logic to think. But we can in the next step I will show you that through molecular dynamics we can calculate this reorganization energy.
Okay, maybe I can ask one question that is really, really basic, but that might be important just for the audience. So I think you skipped very quickly about the interaction. So when you say electronic interaction, how can you explain what it is? Because my feeling is that a lot of people just have some weird understanding of what it is, but it has a pretty well defined, definition, so to say, in math, right? So how can you define it?
What we use in the Hamiltonian,
So this is like an overlap between the wave functions?
Yes, that's I wanted to show you in the where is it? For example, here, this interaction that are represented, I put very, very quickly here, yeah. I didn't write that, but there is coming a term. I put this how is the results of the energy, but here come a term because it's complicated mathematically, but the interaction of is similar to that, but we put the overlapping, exactly the interaction in between and the integral of that between the overlapping of two atoms and or the atom and one state of the metal. And then there is yes, this integral that's the interaction between both.
So if it's okay for you to go to the slide 30, I think 30 or 31, where you show the dependence on the electronic interactions of different theories that you can apply. Actually, it's 38 probably is the right one. So yes, so you have electronic interactions at the bottom, at the x-axis. How can you, is it possible for us from like just as observants, can we really tell if the system has a strong or weak electronic interaction? Just is it like somehow related to chemical bonding that we know from chemistry, for example, chemisorption energies?
It is not so easy because every system had different contribution, and then we have to analyze for every system which are the terms that are taking part of this and give an effect on this interaction. This is not so easy, because we have different orbitals. According if we have a molecule of atoms that are involved different orbitals, the overlap with the metal is different, and depending on the metal, how long is the extension of the orbital from the surface, and all this part are involved in order to obtain this term here is, yes, this integral that give the interaction between the electronic levels of both systems. No?
Okay, so it's pretty involving then to try to predict it. It's not that straightforward.
Yes, yes.
Okay, thank you. Probably we can continue then.
Okay, then okay. Then I shall give now some details how we make this sort of calculation for the electrocatalysis. And we have this Hamiltonian with the component of the different part of the systems, and then for example, this typical reaction, hydrogen evolution, oxidation reaction. This is the prototype of electrocatalysis reaction. In the case of this, we have a Folmer reaction that with DFT, we can calculate the energy and the density of states when a hydrogen approaches the surface. For the case of Tafel, we can calculate when also the energy and the density of state when the molecule dissociate or form. And for the step of Heirovsky, we can calculate what happens when another hydrogen approach to an absorbing hydrogen and form the molecule. But this with DFT are all neutral systems. No? But anyway, this allows us to calculate how strong the interactions are between electrode and the reactant. And that means, I'm sorry, here, with DFT, we calculate this, and how looks this density of states, and from Anderson-Newns, we fit with the equation from Anderson-Newns, the density of states, and calculate the interaction. In the case of the solvent, we assume this parabolic fluctuation of the solvents, and this lambda, we need one lambda that should be introduced in the Anderson-Newns equation. And in order to do that, what we can do is through molecular dynamics, calculate the potential of mean force, and from this calculate how is the dependence of this reorganization energy when the system, solvatic system, approach to the surface. That means we take for solvent coordinate is 0, this is in absence of a solvent. With DFT, we can calculate the density of electronic state for the electrode and for the reactant at different distance from the surface. That it could look like this. No? And then with these fixtures, we use this equation, the Anderson-Newns, in order to obtain the deltas and lambdas. That means this interaction factor. Then what we need, in the first part, I have shown the most of the results were using idealized bands like semi-elliptical band or wide band approximation. But if we obtain the electronic density of states of the electrodes from DFT, then they look like this, and we can use this electronic state for the different bands of an electrode, is P band or D band, to fit the density of state. And then before we had all this form, this idealized form for the reactants at different distances. But now if you use the fit of with the equation of Anderson-Newns for the interaction with the real bands of the metal, we obtain picture like this one. Then with the first easy system to investigate are plane surfaces and from different materials. And for this case, we can assume that the behavior of the solvent or the reorganization of the solvent with the system are similar, at least. And from DFT, we have these different electronic structures. Then, for example, this is the case from DFT, we approach the hydrogen and calculate the density of states. For Anderson-Newns, we fit for every distance the interactions with the electron. And in the case of the solvent, we do molecular dynamics, calculates potential of mean force at each distance, and with that, the solvent reorganization energy. Here it's interesting to see that far away we have our proton is the Sundel ions, and when it approaches to the surface, becomes to be to lose some of the solvation shell, and at the end you see there that the only one water molecule is with this hydrogen, and at the end lose also this one, but there is no more charge. Then these are with the potential of mean force as we calculate for the system, we can obtain this reorganization energy through this equation. The detail where come this equation are in the literature. You can see, I think it's not now to explain so much. And then we obtain this. This is for a case of hydrogen oxidation in palladium 111 surfaces. This is the potential energy surfaces. And if we see here, this is the contour plots of these potential energy surfaces. And these are, at these three different distances, the density of states that we have obtained for the hydrogen atom with DFT at distance from the surface, three different distances. And then with this density of state, we fit using the Anderson-Newns, we obtain the interaction constants. And then the position of this, if we move that due to the lambda that we have obtained for molecular dynamics, and we change the solvent coordinate, the center of this density of states shift according to this. And then we see, for example, by the transition state, this state by Q null is by Q minus 0.6 in the transition state becomes that. But the interaction with the metal is given by this distance. And then far away from the surface, we have practically only the proton. And then this is when we have far away from the surface, a hydrogen atom. But when we move this perturbation of the solvent, then it becomes unoccupied, the orbital of the 1s orbital of hydrogen, and becomes so like a proton. Good. Then we see here, far away, we have actually this Sundel ions, and then when it becomes near at this distance, the density of states change to that, and at the end here have lose practically the half of the solvation shell, and deformed and interacting with the metal, and at the end, at the end, we have the absorbed hydrogen at the metal. But here you can compare, these are the energy obtained from DFT for the hydrogen atoms approaching this surface, and these are the PMF obtained with molecular dynamics. And when the protons start to lose the solvation shell, then the PMF increase and the lambda obviously could decrease the reorganization energy. But these are systems, different systems, different metal with the same orientation, monolayer on metal, and how the electronic shapes of the bands change depending on how are organized this metal. And then here we compare, palladium is a good catalyst, but whole it is not. The activation energy is larger, and we have different systems. One monolayer of palladium on gold. This is still better than the case of palladium pure. And two monolayers are not so good, like one monolayer. And when we have here absorbed hydrogen between two monolayers, the behavior and come a proton, then the behavior is also different. And we can have also one monolayer palladium below a gold layer, and then these are also make difference. These are all different systems where, as example, what we can investigate. But these are interesting today is are nanostructures. We have the improvement in the experimental methodology allows us now to know the local reactivity at different nanostructure. We can use the different methods and obtain STM or a spectroscopic method and measure exactly what happened at a given place of one nanostructure. And then it is interesting to compare with the theoretical calculation of this nanostructure. And but in this case, then we have to take care also that the change of the reorganization energy of the solvation could be very different from one nanostructure to other. And then we have to take into account not only the electronic changes of these different nanostructures, but also, these are different nanostructures, the absorption energy are very different depending on which part of this nanostructure the hydrogen is absorbed. When we have more than one, when the coverage is different, we have more than one side where the hydrogen can absorb. The dependence, you see, the range is very large. We can have a very complicated picture of this. And here we see, for example, for a cluster of 3 palladium atoms, when the Sundel ion approach here, we can see, I put it later, here is start to lose the solvation energy. But in comparison with the plane surfaces, there are still molecules that are around this nanostructure, and the solvation shell still is not completely destroyed until the absorption takes place. And this is good for energy. Here is the other case with a cluster three-dimensional cluster of palladium, and then we see here, then it's coming around the cluster and still have a solvation shell around. And that makes that the PMF for the different nanostructure is also different. And then that means that the reactant can approach the surface, maintaining part of the solvation shell, and this is good to save energy. And then, for example, if here are different some screenshot at different part of the reaction when approach the surface, and we see here for the flat surfaces that when the PMF have increased a lot. That means have lose a lot of solvation shell when I reach the final state. That is not the case in this cluster. The loss of solvation shell is less, and then the energy is again more energy. And well, this is the other one, and then we see that if we compare the cluster with 3 palladium atoms with surface of palladium, here the activation energy is much lower. The same occurs when we have stepped surfaces. For example, silver surfaces. And if we compare what happened, the adsorption on a terrace or near step or over the step, the activation energies are very different in this case, and we can associate not only with that the electronic structure of the sites where it is occurring, the absorption is different, but also with how is the proton solvated in these different cases. Here are experimental data of the Vollmer and Gerischer step on the step or on the terraces, and we have a theoretical calculation. Here we see how is the PMF in a terrace site or in a step site. We see that when the step site remained the solvation shell to a shorter distance until this lose the solvation. And that allows that if this is terraces, then lose solvation energy. Then here we see that the movement is in the parallel to the solvent coordinate. And here at the end, when the electron transfer had occurred, here at the transition state is still far away from the surface. But in the case of the absorption on the bridge side of the step, the proton can approach to the almost to the surface, and then here where the interaction are much stronger, then lose the solvation and occur the reaction with a very low activation energy. Then with hydrogen is relatively simple. The only orbital that is involved is the 1s orbital, but we can have more complicated reactants, like for example, the absorption of OH. Here we have many orbitals that are participating. We have a hydrogen and we have an oxygen. The 1s orbital of this hydrogen here is interacting with the p orbital of the oxygen and forming bonding and anti-bonding orbitals between these two atoms. But when it is near the surface, we see that these two orbitals are interacting with the methyl. These two p orbitals are involved in the interaction with the methyl, and then we can use the fit of this orbital as a function of the distance in order to obtain the potential energy surface. Then we have also the oxygen reduction reactions, and we have investigated that in alkaline medias, the first step, this first step, that's the transfers of one electron, yes, we have see that this is almost an outer sphere reaction, and because it occurs far away from the surface, and on gold and also on silver, and the activation energy is almost similar to the activation energy that predicts Marcus hash model. And we have calculated the interactions parameter between D band and SP band for the oxygen, and we see that they are very low. From the D band is practically 0, and for the SP band is very low. Then other complicated systems, for example, adsorption of cysteine on silver, that we have seen here, the electronic charge redistribution. We see here that are involved. We have bonding orbital between the sulfur and the carbon, and we have this pair of lone pair of electron on one orbital of the sulfur, and how interact this when approach the silver surfaces. And we can calculate also this coupling constant between these different orbitals. And but we see that when the systems are more and more complicated, we have more and more atoms involved, and more orbitals that are involved, and that makes more difficult the calculation. And here we have also investigated that in collaboration with Reinhard Nasmutinov, this the case of electron transfer reactions on graphene electrochemical environment. And we have analyzed what happened with different kinetic regimes. And here it's interesting that the electronic bands are very different. This is the semi-elliptical model that we can assume for a metal. But in the case of graphene, the picture of these electronic states are very different. And we have also investigated what happens if we have mid-gap states that can be obtained perhaps for defects of a graphene layer. And then we see that in the case of a non-adiabatic limit, the red points correspond to the metal that we have seen before, and the green is when we have graphene. But these are the expression for the current, and we see here appears the density of states corresponding to in this case to the graphene. If we have a metal, we can consider instead a semi-elliptical band or the wide band approximation. But the effect is that the curves are very different. And also in the case of the presence of mid-gap state, this curve that are not more had this form that reach a constant value, but can still go through a maximum, for example, and come back. That is very interesting. In the case of the adiabatic limit, also we have difference between the behavior of the metal. This is predicted according to Marcus hash without interaction with the electrode. And in the case of graphene, we have, or graphene with defect, we have this intermediate behavior. If we have a defected, for example, shuffle dislocation, the density of states of these atoms of carbon are different, and then produced as if we put a reactant there, the interaction could be very different from, in the case, this is not so, here the density of states at the Fermi level are very, very low, and then the reactant, there is not so strong interactions. But when states here in the gaps, in the mid gap, appear near the Fermi level, and the reactant is coming in the region where the Fermi level is, that we see that it could be produce a strong interaction. Good. That's this and that, and then I come to the next point. That is this Volcano plots and descriptors, that I want to say some words about that. Usually, the most system that is also apply this Volcano plot is the hydrogen reactions, and actually it is based in the Sabatier principle. That is in the 1920, this very long time ago, and this is said that if a reaction should be better if the absorption free energy is near zero. And this principle that's later in the 50s were taken by Parsons and also by Gerischer, and they try to find correlation between the absorption energy and the activity of reactions. And in the 70s, then Trasati take this topic again, and more recently with theoretical calculation, involving also theoretical calculation, the group of Norskov use these concepts. And this is the original plot of Trasati that applied for the hydrogen evolution reactions. As a function, take that from the energy of hydride formation of methyl. But if we pay attention, all these methyls that are here are not methyl, actually are covered by an oxide. That means that we cannot consider within in the same as the other methyl. Then one part of this Volcano plots disappears, and then we have a Volcano without descending part. Then these are later from Norskov. These are the theoretical values calculated and put again this plot. But here we have again this cover oxide, and we cannot see so like a nice Volcano plot if we disregard this part. And here we have recalculated some and taken some experimental data, and in alkaline media and in acidic media, and then we can distinguish three groups of methyls: these sp methyls, this Koenisch methyl, copper, silver, and gold, and then the D methyls that are good catalysts that have this D band near the Fermi level. But here we see that here the absorption energy actually increased. That should come back, but they don't come back. But because that's in this case change the mechanisms for the hydrogen evolution reaction. The intermediate is another one, and then the reaction is different. That means when we have this Volcano plot, in the case of sp methyl, we can apply Sabatier principle. It's good, but the problem with this methyl is that because they are very, very less active, then in order to obtain the change current, we have to do extrapolation from far away in the potential, and then the error, the experimental error is high. In the case of Koenisch methyl, we have seen here that there is between the three metals, practically there are not differences. They have different absorption energies, but the activity is very similar. And that is because there is a compensation effect. The absorption is less favorable in this direction, but the interaction between the hydrogen and the metal increase in the other direction. And that is this compensation. In the case of the transition method, the reaction occurs through Volmer-Tafel mechanism, and we can distinguish between weakly absorbing hydrogen and strong absorbing hydrogen. And in the case of platinum, the reactions occur through this weak absorbed hydrogen. That is the reason why is not obeys not the Sabatier principle, because we change the intermediate is other. In the case of nickel, the reaction, yes, occurs through this strong absorbing hydrogen, and it follows the Sabatier principle. In the case of nanostructures, it's still more complicated, because here we have this weakly and strong absorbing, two types of different absorbing hydrogen. But when we have nanostructure, we have a lot of possible sites with different absorption energy. And then which of these we choose in order to make a Volcano plot. That is then this is in the case for oxygen reduction. These are the activity plotted as a function of the oxygen binding energy to the metal, to the difference metal. But actually, no, it is not the oxygen, the intermediate. We have to calculate with the real intermediate, that is, in this case, for the reaction, this one. And then there disappears this volcano shape. I like very much one paper that's from Petri and Sirlina. This is an experimental paper, but they do in the 90s a very extensive analysis of the experimental data that at that moment were in the literature, and they they analyze all the types of descriptors that have been used in order to find correlation, and this they look also at the reality of the data. How good are the experimental data? Why? Because if the experimental error is high, and when you have the dispersion of value between different experimental groups, then which value you choose to correlate for the correlation. That is then this myth about Volcano plots and simple descriptors. I should say is good, intense, but there are many questions that we have to take into account when we compare data. The different points that we are comparing have the same right determinant step, is the same mechanism, have the same intermediate, or what is the position of the D-band for different metal, the coupling constant, there are electrochemical effects, geometrical effects, solvation effects. Then it is very difficult to compare data that were not all those things are the same. Another correlation that was very popular is about the D-band center. Is a catalyst has a D-band near the Fermi level, there should be a very good catalyst. That's the message. That is in part true, because they are here when comes a reactant, near the surface and near the Fermi level, then becomes most favorable the reaction. But if we see in detail, there are many things that are not so nice. In the case of the dissociation, for example, without electron transfer, we can see here the dependence of the barrier as a function of the position of the D-band center is almost at the Fermi level. But if we consider reduction or oxidation, these curves are not more symmetric. In the case of oxidation, we see here the most favorable position of the D-band is below the Fermi level. And then depends on how wide is the D-band. We can, that these curves can also cross it. And also, oh, sorry. Here are experimental data, and here are calculated data, and we see, for example, different configuration of a nanostructure of palladium with gold. Here, these three different geometric configurations have exactly the same position, the same center of the D-band, but the activity is very different because there are all other factors that are playing a role there. Here are other correlations according to the nearest relative, the nearest distance, and there are some that work is almost good, but for example, here we see that for the absorption energy, that is the thermodynamic part, there is a nice linear correlation. But if we analyze the barrier for the oxidation or for the reduction of the proton, we see that the correlation with the center of the band is not so wonderful. Then, in conclusion, we can say that Volcano plot is a good attempt to understand some catalytic properties with the aid of a single descriptor, but we must be very careful how we do that. But because we have different intermediates, the kinetics of complex reaction are not so simple. And then here we have seen in the case of the step, for example, that the solvent plays also a role, not only the electronic interaction here, because the solvation is loose at the terraces very early. Then when in the transition state, the reactants are far away from the surface and the activation energy is larger. When it's in absorption comes to a step position, then can reach more and more near the surface, and then the interaction here is much stronger, and then can occur the reaction. We see here, for example, also platinum and nickel, they have very similar D-band structures. Also inclusive nickel look like have more electronic state near the Fermi level. However, platinum is a very large atoms, and the orbitals stand far away from the surface. Nickel is smaller, and then that's produced that the interaction between the electronic states of the metal with the reactant, in the case of platinum, are much larger, also at larger distances than nickel. That is the reason why platinum is a better catalyst than nickel. Good. This is what was here, and then we can very nice. It should be very nice if we can discuss what are the perspective of improvement challenges we have take into account for the future. We have always these components of our systems, this the electrode, the solvent, and the reactant, and how we can describe that. the goal should be use a realistic model that treat all these parts in the same atomic detail. But what is the state of the art? In the case of DFT, we can extend, DFT can explain very good the electrode and the reactant, the electronic structure, but in which way we can extend that to the thin layer of solution. There is an improvement in the case of ab initio, molecular dynamic. Axel Gross have shown very nice results in this direction, but this is not so easy to treat that. What happened with the electrode potential? How we describe the electrode potential by DFT? If we have electron transfer reaction, DFT, we need a neutral system. How we consider electron transfer reaction? These are many things that are not so easy to obtain a solution, to obtain a good approximation. There are some attempts, but still I think we have to work hard in this direction. The other approach, we can use classical molecular dynamic for the solution, but what happened with the reactant and the method, we cannot use that in the same level. In our approach, we try to make this combination from DFT and molecular dynamic in the frameworks of the Hamiltonian, the modern Hamiltonian. But it is also not the perfect approach. We should be nice to improve that also. And recently there are some promising approach that has used DFT-based constrained molecular dynamic simulation, and this could be perhaps a good direction, but these are very costly and in computing time. It's not so easy to model electrochemical interfaces in this way. And then, good, I think I finished now. I want to acknowledge all the calculations in the Baden-Württemberg clusters, access to the computer, this Justus cluster. And I want to also thank especially Professor Axel Gross, because I have to tell you, since end of September, my contract with the Ulm University had finished, and it couldn't be renewed, extended, because there are not enough funding to pay me. And then 2 years before my retirement, I don't have any job more. Then I have applied for at the German Research Foundation for my own position, but okay, I am waiting for the decision. I hope I will be successful. But yes, Axel Gross gave me the opportunity to stay still at the university as a guest, and then I have access to the computer center. I have my email. I could do this seminar, and okay. But then I want to show you also the collaborators that I have during my scientific life, not in the last time at least. Most of this theory of electrocatalysis I have developed together with Wolfgang Schmickler. Then with Axel Gross, one of my fruitful period of time in my scientific life was during the existence of this network, that is a research group where many people were working in collaborations. And then at that time, I have my own project, my own group, and that was very nice. Obviously, Fernanda Juarez was I want to thank her because she was a co-worker for a long, long time. These are my 3 last PhD students in Argentina. These 2 had finished, and she is writing down, and she will be ready soon. And then, okay, in Argentina, I have the collaboration with Paola Cuaino from Santa Fe, Ezequiel Leiva from the chemistry department in Córdoba, Horacio Pastaski in physical department in Córdoba. And then here in Europe, with Mark Copper, we started with the bone breaking, so in the some at the beginning of the development of our electrocatalysis theory. And then Anna Ignaciak from Lodz in Poland, we have worked together in the oxygen reduction reaction. Of course, Renat Nasmutdinov, that is coming here to Ulm every year, and we were also in Kazan, and we have a long-term cooperation in oxygen, and in the last time with graphene. Elena Sabinova in Strasbourg with the nanostructure, and in China we were also there by invitation of Jian Chen, and then we gave there a course about electrocatalysis. That's a lot of elements of this course I have taken for this colloquium, but okay, that would took 3 months. Here there are 2 hours. I have to compress that. But this is one of her students that now is here in Germany. And okay, then I have applied for this project and this German research foundation, and I hope it should be successful. But these are some of the very, very previous work that I tried to do is in part of this program. Then the oxidation of hydrogen from graphene, how goes to the water phase and form this Sundel ion, and then I have tried to do that at the same level the treatment. But this is my project. These are not published, and we have to optimize that. And I hope I am successful, and I can tell you about that in some time. Or in other case, this perhaps is my last talk in my scientific career, but it was very nice that was this, if that is the case. But thank you very much, and I am open for questions, comments, and.
Thank you so much, Elizabeth. This was great talk, absolutely great talk, and I think it also shows how many people actually are involved in big science and must be involved to make it happen. And we all hope, of course, that you will be able to give more talks.
I hope also.
Yeah, I can't speak for the colloquium side, but
yeah.
Okay, so we are open to questions, and I can already see a question from Cyril. So he is asking, well, basically the question that I had also for you, it's about the inclusion of the double layer effect. Mm-hmm. So do you include it, like the fact that you should have certain cations or anions at the surface counteracting the electrode potential, or you just include the potential as sort of the level position of the reactant with respect to the Fermi level of the system? And the other question that is related to it is, does it make a difference in particular for charged versus neutral substrates? For example, the proton reduction versus O2. By substrate, I think he means that the molecule. So if you have a proton reduction or O2 reduction, does it make a difference to have a double layer or not?
Yes, these are very interesting comments, and yes, that is so. We have used the potential is only a shift of the position of the electron level of the reactants. we don't take into account some changes in the double layer structure that could take place at the same time. Also, or the co-adsorption of anions or other species. That could have an influence, and then this is the what I want to do perhaps in the future, to include a more detailed description of the interface in this electron transfer reaction. If okay, that's are the plan, but at the moment these are only this, and obviously if we have a charged species, the interaction should be also different. Yeah. With DFT, we have calculated only the interaction of the neutral hydrogen when it's coming to the surface, and then it becomes charged when we move this electronic position due to the solvent interaction. But we assume that the interaction is the same. But this is an approximation.
Sure, yes. And the type of functional that you use for the description, you have to include it as in a double layer description in some way, right? Because when your charge is approaching the surface, the last few angstroms, it experiences the charge, the potential variation, which you should describe using some sort of a functional. So is it a linear description that you always use? Or because I remember there were some papers that involved I think the exponential dependence and some other types of functionals, which I was just curious which one is, of course, it's very approximation, but still, is it the way that you can still include, for example, the type of cations that are co-adsorbed? For example, they're bigger, smaller, so you can make that functional different as a result.
Yes, these are things that we have to improve. That is, yes. We assume that the interaction with the solvent that depends linearly with the charge, when through this reorganization solvent. But with the methyl, we use the DFT with the usual functionals and so on. Then we don't take into account that.
I see, and maybe I will have two questions relevant to the last part of your talk. So the first one is regarding the approach where the Volcano plots are calculated. So this is the pure DFT calculations is what a lot of people do these days. Mm-hmm. And these just provides thermodynamic quantities. So for example, an energy of adsorption.
Yeah.
Now, your approach, of course, includes the actual activation step, which means that you can calculate the kinetics more or less directly.
Yeah.
So now, but from the adsorption energies, what people normally do is they can say something about the activation energy. This is exactly through this Sabatier principle. So quantitatively, can you tell us what is approximate, so the order of magnitude of the error that people can get, or you can maybe outline between the two approaches. So if somebody uses adsorption versus somebody using this more or less complete theory of DFT plus MD plus modal Hamiltonian. So it's an order of 1 electron volt or like 0.1 or 0.01.
For example, perhaps this plot can show you something about that. Because the blue points are the absorption energy. That's we can calculate with DFT when for this different system, hydrogen on gold 1 on the palladium between gold, and all these different systems, and this as a function of the D band center of all this system, and this the absorption energy is almost linear. We can say, oh, okay, correlation is very good. But if we can, for every of these systems with the potential energy surface, we can calculate also the barrier for the reaction, for this reaction, for the oxidation, and also for the formation of the absorption hydrogen from proton. And these are the other points, these black points and these red points, and correlated with the D-band center. And we see that the results are very different. And we cannot analyze only the absorption energy. We have to take into account the barrier. And to calculate the barrier, we need a model that's more complicated than only DFT.
So the error can be exceeding 1 electron volt potential.
Yes, yes, of course.
Okay, I think that is quite important to keep in mind. And the second question that I have is related to the slide 120. I think you were discussing the adsorption and interaction parameters.
Which slide?
120.
120. This one?
Yes. So you say for the coinage metals,
yes.
The last two sentences are the adsorption is less favorable, but the interaction with hydrogen increases. And this is why, so they counteract basically each other. This is why you don't have very good HR on gold.
Mm-hmm.
So my question is this: do you see any ways, at least as a theoretician, to decouple these two effects? Because if we could, then of course we could make completely new catalysts.
Mm-hmm. Good. This the nature is so we have this absorption energy, and we have the interaction, and this we cannot separate that. This, we see that absorb better on copper and silver and gold, but the interaction is this how it interact, the overlapping, for example, that depends also the how large is the metal, how expanded. I have shown also in the case of platinum and nickel. This, the orbitals extend more far away from the surface, and then that favors the good interaction. And if the system, the atoms are small and this is lower, the extension, then it's bad. But we cannot change this. This is the nature of this system.
So even if we have copper monolayer on gold, we can have copper orbitals, but gold density of states. Yeah. Isn't it the way to decouple it?
Good. We have also tried that. Some of them I have shown some very quickly that, but we have investigated the different substrate and put another metal that could be better active, but then change also the distance between the neighbors of the metal. And in that case, we have also made some theoretical experiment in the case that we use, for example, for palladium, we put the lattice constant of gold. Then we have only palladium, but with the separation that we have on gold. And in that case, the activity is not the same as we have with the monolayer on gold. Because there are interactions also between gold and palladium that have an indirect effect on the reaction that takes place there. And this is a paradigmatic perhaps example, but because we try to separate that and then to have again the same in the case of gold, but play a role this other interaction, and then make an effect on that. That is the problem. Also, with this system, we cannot simplify it in a very good, nice way. These are all are interrelated. The solve in the electrochemical environment is so complicated. That involves the interaction with the solvent, the interaction with the metal, the reactant, the anions. It is a very hard task to separate the contribution.
Okay, no, I fully agree. At least we know how they can be related to some extent. This is already good. So, Elizabeth, thank you so much for being with us today. It was really great. It was great to have such a long discussion about the theory that I've been looking forward to, for sure, in this colloquium. And I'm really thankful for everyone to stay till late. It's been more than 2 hours. Thank you so much for a nice colloquium.
Yeah, I'm sorry, but it was to take too long. But it's very difficult to compress it.
It's important to be explicit when you discuss this kind of theory.
Okay.
Yeah. So with that, we are ending our fall semester, and next semester will start in hopefully in January or February. I think in February, and we will announce the list of speakers very soon. It will be as exciting as this one. And please, so stay tuned. Thank you.